Okay, welcome back. Yesterday we have seen the kind of stereoelectronic requirements that are imposed in some reactions, especially substitution, elimination and rearrangement. And we have seen that there are the stereoelectronic requirements actually, and along with conformation that dictates the major product formation. Okay. Now, let us go into another very important topic now, stereoselective and stereospecific reactions. Okay. Along with that, we will also discuss the asymmetric synthesis. Now, suppose you have two compounds, two isomers A and B, these are stereoisomers. And if there is a possibility of formation of C and D from the stereoisomer A, and the relationship between C and D are also stereoisomers, and suppose the same C and D can also be obtained from B. So, what are we are talking about, that we have taken two enantiomer, two stereoisomers A and B, and we are doing some reaction on these two compounds, and suppose the possibility of product formation is designated as C and D as the products. So, if there is a possibility of C or D or both C and D formation from A, and the same thing also happened from B. So, basically the two stereoisomers can give rise to the same set of stereoisomeric products. Now, what can happen in many cases, suppose A only gives C and B only gives D. Okay. Then that reaction, that means one set of stereoisomers is gone in the product. So, only one major stereoisomeric product is obtained, A going to C and not D, and B also is going to D, or B can also go to C. So, lot of possibilities. Suppose C is the only product from A, or that means out of the two diastereoisomers here, the stereoisomers, you have only one of them is formed on the reaction when the reaction was carried out on E. So, this reaction will be individually called a stereoselective reactions, because out of the stereoisomeric products that are possible, only one is obtained. That one can be in a meso form, or it could be an optically active pair, both are possible. Okay. We will discuss examples, this point will be clear. So, basic definition is that whenever a reaction is done on an isomer A, and then if there is possibility of formation of more stereoisomers, and if only one stereoisomer is obtained in the product, then that reaction is called a stereoselective reaction. So, it could be C is the only product or D is the only product, both are possible, but in both the cases the reaction is stereoselective. Similarly, if B gives C or B gives D, only one, not both, then the reaction is also individually stereoselective for with respect to B, that means B is undergoing a stereoselective reactions. Okay. So, I hope this is clear. That means, if I take one compound and from that compound if there is a possibility of generation of different products, the products are related by stereoisomerism, and if only one product is obtained and not the other, then that is called as stereoselective reactions. Okay. Now, actually in the organic chemistry books, these terms are frequently used in place of one another. However, what I am talking is the strict definition of a stereoselective reaction. Now, suppose what happens that if B, see A and B are stereoisomers, and suppose A gives C and B gives D. If A gives C and B gives D, that means the reaction are individually stereoselective, because only one set product is obtained. The other important thing is that the product formation is dependent on the stereochemistry of the starting material, because now these are two stereoisomers. So, depending on which isomer you are taking, that will decide which product is being formed. So, A giving C and B giving D, and relationship between these two are stereoisomers, and relationship between these two are stereoisomers also. So, what I am saying that the stereoisomer that is obtained from the reaction of A is different from the stereoisomer, that is D here, obtained from B. That means, your product formation is dependent on the geometry of the starting compounds. If that happens, then that is called a stereospecific reaction. So, stereospecific reaction points out to the stereochemistry of the starting materials, because the product formation depends on the what is the stereochemistry or the geometry of the starting material. On the other hand, stereoselectivity is dependent on which dependent on just the number of products that you are getting in the reaction. So, if one product is obtained, the reaction becomes stereoselective. Now, I give you one example. Suppose I take cis 2-methyl butene, and if I add bromine onto this, say I take bromine in carbon tetrachloride, I know the bromine atoms add, and the bromine atoms add in a trans manner, right, in an anti manner. Okay, I can write. That means, one bromine, if it comes from the top, then the other bromine comes from the bottom. Okay. And that is because of the formation of a cyclic bromonium ion. Okay. Now, if that be the case, so the product that you will be getting is, so one is this, when the bromine approaches from this side and the other bromine approaches from the other side. So, you get this compound, plus you will get the other compound, the other possibility, the Br coming from this side and the other Br coming from the other side. Okay, so, you get Br here and you get methyl, you get hydrogen, and then you get Br on this side, and then CH3 and this H. Now, these two are racemic mixtures, they are optically active, but both the compounds are formed in 1:1 amount. Okay. Now, there is a third possibility, the third possible compounds with this formula is the Meso compound, which has a plane of symmetry, that we know. This is the Meso, but what is obtained in this addition, trans addition of bromine, that you get only these two. Okay. So, these two are one enantiomeric pair. So, you get one enantiomeric pair and not the Meso compound. Okay. So, this reaction is stereoselective. Remember, stereoselectivity does not discriminate between the extent of the enantiomers. Even if you get plus minus 1:1, the reaction is stereoselective. That means, this is considered as one set, and this is the other one, the other set, but here it is not set, because it is a Meso compound. So, it exists only in one isomer. However, if you get either this or this, the reaction becomes stereoselective. So, here you are getting only this compound. So, it is stereoselective. Now, if you take the trans compound, the trans alkene, then what will happen? after bromine addition, if the bromine adds from this side or that side, so you are, I erase this, actually that is not the way to write, you will get a compound which will have a center of symmetry now. So, one bromine comes from here, another bromine comes from the other side, and now you have a center and I present in the compound. Okay. So, it got has an I. Okay. It also has a plane of symmetry, but not in this conformation. In the eclipse, fully eclipse conformation, you get the plane of symmetry. So, it has got I. So, this is now you are not getting the DL pair, you are not getting the DL pair. So, that is not obtained. So, what you get is the meso. I am not doing the other side of addition, because that gives the same product. Okay. Now, you can have a very see which product, which will give which product is there is a mnemonic device you can apply, that because the bromine adding opposite, that means that will have a, that will bring a I at this point, but this molecule does not have I. So, what happens? It has sigma. So, if the bromines add from the same side, the sigma is retained, but the bromine is adding from the opposite side. So, the sigma is disrupted. So, that is why you get an enantiomeric pair. Here already I is present and bromines are adding in a center of symmetric fashion. So, it will, the I will be maintained, will be retained, and you get the meso compound. So, this is what is stereo, both the individual reactions are stereoselective, and overall reaction bromine addition to alkene is stereospecific also, because the product depends, the product geometry depends on the geometry of the starting material. Okay, that is clear. Now, let us take an example. If we do the same reaction with cyclohexene, see I am talking about the very see, if you are very pure stereochemist, then this is what is followed. That means these terms have to be followed very seriously, very rigorously. Like when you say that bromine addition to cis or trans to butene is stereoselective as well as stereospecific. Okay. But that is only meant for the butene system. If you take the cyclohexene system, the bromines will add from the opposite sides. So, you get bromine here, hydrogen there, bromine here, hydrogen there, because they will be adding in a trans fashion. Now, this is one product, and you get the other product, because this is now optically active. So, hydrogen, bromine, bromine, hydrogen. So, this DL pair you will obtain. Okay. Now, what was the other possible product? The other possible product was the meso. But this is not obtained. So, this is not obtained, only one pair, enantiomeric pair is obtained. So, the reaction is stereoselective. Now, the question is, if the reaction, if the question is asked that is this reaction stereospecific. Now, to know that answer, you have to make the other isomer of cyclohexene, this is the cis double bond. So, you have to make the other isomer of cyclohexene and do the same reaction and see which product is obtained. That means, you have to make the transform of like this, but this 1, 2, 3, 4, 5, 6, this does not exist. This is sterically not accessible, does not exist. Why it does not exist? Because you cannot introduce a trans double bond and make a 6-membered ring. See, basically these are the 4 carbon atoms already gone, and if you want to make the trans compound, so then you have only 2 more carbons, and this is not possible to add like this. So, you need, later on you will be knowing this, or you should know this, that it needs total 8 carbons, that means 4 carbons more to introduce a trans double bond in a in a cyclic ring. So, trans octene is the first one. Of course, this does not exist in this form, this has a special geometry and this is optically active, but just to know that trans double bond exists only when n is the number of carbon atoms in the ring, when n is equal to 8, greater than or equals to 8, okay. Then you can introduce the trans double bond. So, this compound does not exist. So, you will not be able to do this bromine addition onto this and see what happens. This is not possible, nobody has done that, and nobody could do that because this does not exist. So, now according to the strict definition of stereospecific reaction, you cannot say that this reaction is stereospecific, okay, because simply to know the stereospecificity you have to take both the isomers, both the substrates and do the reaction, and one substrate should give one product, another substrate should give another product, then it is stereospecific. It is the reaction is stereoselective because there is no problem, because out of this is pair DL pair and this is the meso, you are not getting the meso, you are getting only this diastereomeric pair. So, this reaction is stereoselective. Okay. Next is the question of asymmetry. Okay. Asymmetric synthesis. What is asymmetric synthesis? In true sense, see, as I said, all these terminologies have been quite misused in the organic chemistry textbooks. Okay. But what I am telling today is the actual meaning of these terms, but later on we may also as we go along the terms can interchange with each other like the books are doing, but it is better to know the exact meaning of this and try to avoid those type of complications by using randomly one over the other. Okay. That should not be done. Now, what is asymmetric synthesis? Asymmetric synthesis is if you take a molecule and if you have a pro-stereogenic center. Pro-stereogenic center means or if you just do not forget tell about pro-stereogenic center. If you have a molecule where there is a carbon, suppose a carbon is there, and if you want to convert this carbon, it was symmetric carbon, and you want to make it asymmetric. If you want to convert it into an asymmetric carbon. So, a symmetric carbon is converted, or an achiral center, I can say an achiral center is converted into a chiral center, or the modern terminology is a stereogenic center. Now, when you make this chiral center, so there is a possibility of formation of R and S configuration, okay, both, and usually both are formed in 50-50, that is what is expected. But if you can do it in such a way that only one of these is the sole product or could be the major product, then that reaction will be called an asymmetric synthesis. So, what I am saying again, that if you convert an achiral carbon into a chiral carbon, and if you get only one configuration as the major one or even possibly 100%, then that reaction will be called, the reaction that you have taken help to do that will be called an asymmetric reaction. Okay. Will be called an asymmetric reaction, and if it is a part of a synthetic protocol, that is called an asymmetric synthesis. Okay. Now, there is a thing of degree of asymmetry. As I said that you can get 100% of this, almost 100%, or you can get 90% of this, 10% of this. Okay. So, there is a thing that is called degree of asymmetry, which is expressed in terms of, you remember I gave you what is called enantiomeric excess or optical purity of a molecule. That optical purity or enantiomeric excess will tell you, or even diastereomeric excess, if they happen to be diastereomers, in this case enantiomers, but there are cases where the product can be diastereomers. So, that diastereomeric excess or the enantiomeric excess or the optical purity will tell you about the extent of asymmetry that you have achieved during your reaction. Okay. Now, the question is, how can you achieve how can we achieve this type of asymmetric synthesis? Suppose I take a carbonyl compound. Okay. Suppose there is a methyl, suppose these two groups are different, R1 and R2. Okay. Now, I have told you earlier that whenever you have this, better way is write that the carbon is in the plane of the board, then these two carbons, one will be, so this is vertically placed. So, the R1 this is vertical to the double bond to the board. So, that is placed along this line, the carbon oxygen is in the plane of the board, but this R1 and R2, there one is going this way and the other is going in the back side. Okay. So, R1, R2 and this carbon and oxygen, that makes a vertical plane, but with the carbonyl is in the plane of the board. Okay. If it is placed in that way. Now, what happens? I know that carbonyls are susceptible to nucleophilic addition. Okay. So, suppose I add a nucleophile. Now, whenever I place the carbonyl, now you have two faces of the carbonyl. The nucleophile can approach from this side or the nucleophile can approach from this side. Okay. Now, what are these sides? How do you define these sides? We have seen the ray and the psi face. First of all, these faces are either enantiotopic or diastereotopic, depend on what type of products you ultimately get there. Okay. If you end up getting enantiomers, then there will be enantiotopic faces. Suppose these two are not chiral, they are achiral groups. Okay. Suppose these two groups are achiral groups. Say take an example, suppose methyl, this is methyl and this is ethyl. Okay. Now, the top group, you know how to number this, the top group is the top face is now 1. If you do the preference, the priority sequence, this is 1, this is 2 and this is 3. So, if you see from the top, so 1, then 2 and then 3. So, that means it is going in a clockwise direction. So, this is a ray phase. Okay. This is a ray phase. And if you do if you check this one, so this is 1, this is 2 and this is 3. So, now it is going in an anti-clockwise direction. So, this will be psi phase, that we have done earlier, right. This is ray phase and that is psi phase. So, if the nucleophile approaches from the ray phase, then the product will be C2H5 carbon and this will be OH and sorry, now the nucleophile will be on this side and OH will be on that side. Okay. And if this is the ray phase approach and if it is from the psi phase, then the product will be, this is OH, this is nucleophile and this is methyl and this is your ethyl. So, what is the relationship between these two? They are mirror images. Okay. They are enantiomeric pairs. That is why I called this as enantiotopic faces. Okay. Now, the transition state that is involved when the attack takes from the ray phase, you can depict it as without much deformation. You can say that the carbonyl oxygen has broken to some extent and this is the C2H5, this is the nucleophile. So, that is forming a bond, half bond. So, this is the transition state. Okay. So, that will be delta minus, and if it is approaching from the psi phase, the transition state will be so C2H5 and now the nucleophile will be from this side. Okay. The nucleophile actually approaches at an angle of about 107 degree. This is what is called Burgi-Dunij trajectory. So, whenever something attacks to a carbonyl, see this is a carbonyl carbon, this is a carbonyl carbon, suppose this is oxygen. So, the nucleophile does not approach at perpendicular direction, it approaches at an angle of about 107 degree, close to the angle of an sp3 carbon. Remember that this carbon after the addition will become an sp3. So, it is close to that sp3 carbon. So, this trajectory is called Burgi-Dunij trajectory, and the angle is calculated to be around 107 degree. So, that is why I make it slightly slant in that sense 107 degree. Now, the important thing is that these two are now mirror images. These two are now mirror images. So, energetically they are same. So, same energy. So, same energy. So, if you do this type of reaction where the transition states are enantiomeric, that means you start from the carbonyl, that is your carbonyl compound, that is the ethyl methyl ketone that we have started, and what you are getting two products. So, one product is, suppose this is the R compound and this is the S compound, but the problem is both S and R will have the same energy, but here the problem is the transition states, and this is the transition state, this is transition state for R compound formation, transition state for S compound formation. These transition states are enantiomeric. If that is the case, that means they have same energy, and if that be the case, this is your substrate, that means the starting ketone. So, the activation energy for the formation of the R compound is the same as the activation energy for the formation of the. So, this is the delta E, this is delta E, they are same. So, delta E R and delta, so this is delta E R and this is delta E S, make a star, maybe a hash. So, these two are same. So, if these two are same, then the rate of formation of R will be equal to rate of formation of S, and that means your R and S will be produced in equal amount. So, R by S will be dependent on rate of formation of R is, and that will be equal to rate of formation of S, because both have the same activation energy. Okay. So, this is asymmetric synthesis, because what is asymmetric synthesis? If you can make one of these as the major product, then that becomes an asymmetric synthesis. Okay. But this way you cannot achieve this. If the transition states are enantiomeric, then you cannot achieve asymmetric synthesis. So, you have to introduce diastereomeric relationship between the transition states in order to achieve an asymmetric synthesis. So, that is the principle of asymmetric synthesis, that when you consider the transition states cannot be enantiomeric. So, they have to be diastereomeric, and you know the diastereomers have different energy. Okay. Diastereomers are not mirror images, that is why they are called diastereomers, and they have different energy levels. And if they have different energy levels, then the activation barrier changes for the formation of both the compounds, and then there is a possibility of formation of one compound over the other, one configuration over the other. So, that is the principle of asymmetric synthesis. That means, whatever you do, you have to make these transition states differ in energy. Okay. Differ in energy. Suppose this will be bigger and this will be smaller. Now, the question is how do you do it? Okay. So, this is what is, then this will not be equal to, this will not be equal to this, and if that is not equal to this, this is not equal to 1:1. So, you have an asymmetric synthesis. The question is what is the degree of asymmetry? That depends on the type of reaction that you are doing. Okay. So, to achieve asymmetric synthesis, the transition states, the rule of thumb is the transition states should be diastereomeric. Okay. Then only you can have an asymmetric synthesis, because then only the rate of formation of one compound over the other will be different. Okay. So, in the next lecture, we will consider how to achieve asymmetric synthesis with some examples, and then how to predict which compound or which diastereomer or which isomer is obtained in major amount over the other. There are certain rules which governs the which can predict the configuration of the major configuration, but that will be in the next lecture. Thank you.